to Mars continues. The perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
NASA's Mars Perseverance rover left Earth 6 months ago. Now we are gearing up for touchdown on the Red Planet in just a few weeks. The rover will attempt to land in Jezero Crater on February 18th. It's the most difficult landing site on Mars ever attempted, but the Perseverance rover and the team are ready. Welcome to NASA's Jet Propulsion Laboratory in Southern California. I'm Raquel Villanueva. Today we are here to talk about Perseverance's mission. We will go over the challenges the team has faced and the challenging landing ahead. We will also talk about the mission's science goals and how Perseverance fits into NASA's future plans for Mars sample return. On our panel today are NASA Associate Administrator Thomas Zurbuchen, NASA Planetary Science Division Director Lori Glaze, Perseverance Deputy Project Manager Matt Wallace, Entry, Descent, and Landing Phase Lead, Al Chen, Perseverance Project Scientist, Ken Farley, Perseverance Science Team Member, Bryony Horgan. For anyone watching who'd like to submit a question, you can do so by using the Countdown to Mars hashtag. Our phone lines are now open to the media. You can ask a question by pressing *1. I'd like to start by welcoming Thomas Zurbuchen.
Hey, thanks so much. I'm so pleased to be here today as the Perseverance rover makes the final kilometers on its long journey to Mars and the landing on February 18th. I want to note for a moment the place where we find ourselves. A place where a mission to Mars and what all of us do in science and exploration provide hope and unity. Vice President Harris said, "Even in dark times, we not only dream, we do. We don't only see what has been, we see what can be. We shoot for the moon and then we plant our flag on it. We are bold, fearless, and ambitious." End of quote. At the request of the new administration, a rock from the Apollo 17 mission was delivered to the White House on loan on display in the Oval Office. A recognition of the bold, fearless ambitions and accomplishments of earlier generations, and the symbol of the new administration's support for America's current moon-to-Mars exploration approach. And Perseverance is at the forefront of that work. As our cosmic neighbor and as a destination, Mars continues to captivate our imagination, both as scientists and as explorers. And it seems every time we learn something new, we uncover more questions. We know that Mars had a wet past, and we used our Spirit and Opportunity rovers to follow the water in search of answers as to why this once ocean world is now dry and desolate. Following those missions came our Curiosity rover, which landed on Mars in 2012 and is still operating today and constantly sending back data about the complex chemical composition and history of Mars. We have additional missions in development and formulation, but the Mars 2020 Perseverance rover is the next step in a logical progression that NASA has strategically pursued with Mars exploration, and it builds upon decades of knowledge, experience, and unique expertise. Perseverance is our robotic astrobiologist, and it will be the first rover NASA has sent to Mars with the explicit goal of searching for signs of ancient life. It will build upon what we currently know from our previous rovers, orbiters, and landers, and it will attempt to answer an age-old question that has eluded humanity for generations: whether life has ever existed elsewhere beyond our own planet, our Earth. Perseverance also will help enable human exploration of the planet in the coming years as it demonstrates new and more precise entry, descent, and landing technologies. The MOXIE instrument will show us how to produce oxygen on the Martian surface from the atmosphere, and many other aspects of our science instruments will inform the future journey of astronauts there. Our rover also carries the Ingenuity helicopter, which will be the first aircraft to attempt controlled flight on another planet, a true extraterrestrial Wright brothers moment. The rover exemplifies the spirit of exploration as it pulls on science, technology, and human exploration to work to advance our goals in many areas. And Perseverance, by its very name, describes the human spirit that gets us there. Landing on Mars is hard enough, and while we are all eagerly awaiting the day next month when Perseverance safely lands on the red planet, it is not guaranteed that we will be successful. It's very hard. While we hope that the situation on our world with respect to COVID would have improved since launch, it has not. And that has meant that we've needed to be flexible and adapt to keep working safely and effectively. Regardless of everything that has happened due to COVID, it is the constant innovation, dedication, and above else, unity of this team that has allowed work on the Perseverance rover to continue in a safe manner. And now the world can join us once again as we attempt to do one of the hardest things ever done by humanity, and certainly in space science. Success does not come easily, and it's only due to the efforts of this team that we are here today to talk about this next step in Mars exploration and planetary science. You'll hear my colleagues on this panel talk about the difficulties of landing, the technologies that make it possible, and the hope a successful landing brings for finally bringing a sample of Mars home to Earth. But the journey of Perseverance also begins with a successful touchdown. It only begins that way, in fact. Then the hard work and the long-term perseverance really starts. That's because Perseverance is also the first step in our round-trip mission to Mars. Our rover begins an ambitious international campaign with the European Space Agency to bring pristine samples from Mars safely back to Earth through our Mars Sample Return campaign, which you'll hear my colleague Dr. Lori Glaze speak about in more detail. At NASA, we are dedicated to the peaceful exploration of space for the benefit of humanity, and we are dedicated to inspiring the next generation of explorers. Science has the power to unite us as it transcends language, borders, and many boundaries of many types. This mission could not have a better name, Perseverance. And it is my sincere hope that this mission will inspire all of us, all of you, to persevere together in hopes of a better tomorrow. Now I'll turn it over to Dr. Lori Glaze, Director of the Planetary Science Division, to tell you more about why we want a sample of Mars and how we'll get it done. Lori?
Thank you, Thomas. I am thrilled to be here today as our countdown to Mars winds down from months to just weeks. Perseverance is closing in on the red planet, and our team is preparing for her to touch down at Jezero Crater. After an incredibly challenging year filled with high stakes on a world stage of uncertainty, I am so proud of the men and women across all of NASA. Their focus, dedication, and resolve never once wavered. They are the epitome of perseverance, and they are the heart of perseverance. This epic mission that exemplifies NASA's vision for science to lead a globally interconnected program of discovery that encourages innovation, positively impacts people's lives, and is a source of inspiration. As the next bold step in our Mars exploration program, Perseverance is the most advanced mission humans have ever sent to the red planet's surface. To say we're pumped about it, well, that would be a huge understatement. One of Perseverance's primary objectives, supports the field of astrobiology, which is the study of how life comes to be, the environments that can support life, and the search to see if life exists anywhere else beyond Earth. Perseverance is the very first rover designed to seek signs of past microbial life by collecting and caching rock and soil samples that will be returned to Earth by future missions. Her robust set of advanced instruments will also look for evidence of ancient habitable environments and monitor environmental conditions, all of which are paramount to increasing our understanding of how to protect future human explorers. Mars is a keeper of deep scientific secrets, which the rover will help unlock by studying the ancient record preserved in the layers of rock on the planet's surface. Scientists will be looking for rocks that may have formed in water, possibly preserving evidence of the chemical building blocks of life. For generations, scientists have wanted a sample of Mars to study. While we do have Martian meteorites here on Earth, it's much different than having samples of Mars rocks and soil that are pristine and that we know exactly where they came from. Samples from Mars have the potential to profoundly change our understanding of the origin, evolution, and distribution of life on Earth and elsewhere in the solar system. Even now, NASA continues to study moon samples returned by the Apollo program more than 50 years ago. We expect samples of Mars to provide new knowledge for decades to come as we study them with state-of-the-art laboratory tools we couldn't possibly carry to Mars right now. We may even see a sample of Mars displayed in the Oval Office one day. But first, we need to bring the samples back to Earth. The plans for Mars sample return are multifaceted and complex. But it's exciting how our technologies have matured, bringing us to this point where we can now attempt this amazing feat. To be certain we are ready, NASA initiated an independent review board to determine if this long-awaited mission is positioned for success. The board concluded that NASA is indeed prepared for the campaign, building on decades of scientific advancements and technical progress in Mars exploration. This historic endeavor demands multiple spacecraft and our partnership with the European Space Agency working together with a carefully orchestrated approach. Let me show you how. First, Perseverance will drill and prepare samples for return and cache them on the surface of Mars. In 2026, a fetch rover will be launched to collect those samples and bring them to a rocket that will launch them into orbit around Mars. Another orbiter will rendezvous and capture those samples for safe delivery to Earth. If it sounds complicated, it is. If it sounds extreme, it most certainly is. The Mars sample return mission will also help us prepare for human exploration. Things like the precision landing technology, capability to launch the first rocket from the Martian surface, and being able to assess soil characteristics and toxicity are all essential to paving the way for the health and safety of our human explorers. The technology to return the samples that Perseverance collects is maturing, but NASA's investments in developing autonomous robots and landing large payloads on Mars have laid the groundwork for a successful sample return campaign. We are so thrilled to be working with ESA on Mars sample return and with partners from Spain, Norway, and France on Perseverance science as we take our next steps in exploring the solar system. It's taken a lot of work, and there is much more work to do. But if there's one thing the Perseverance engineers and scientists have proven is there's just no I in team. I'll throw things back over to JPL, where Matt Wallace will talk about his team and give a project overview.
Thank you very much, Lori. Thank both you and Thomas for your kind words about the team, first of all. I've worked on every Mars rover mission. This is my fifth one. And Perseverance is different in many important ways. I wanted to touch on some of those for you to start this off. First of all, this is the biggest vehicle we've ever attempted to land on Mars. It weighs in at over 1 metric ton, and it is carrying 50% more science and technology payload than Curiosity, its closest relative, which landed in 2012. There are a number of new landing technologies on this vehicle, which Al Chen, my teammate here, will talk about shortly. But these technologies have been critical in allowing us to send this vehicle in the Jezero crater, a scientifically important location, but also a difficult place to land on Mars, and a site that was considered on previous missions but rejected. We can now get there with our technologies. We're carrying really an exquisitely complex and sophisticated set of new instruments to the surface of Mars for the first time. These are the instruments which our project scientist Ken Farley will tell you more about, but they're going to allow us to do the best job we can to understand that environment we land on and to pick the best samples, very limited number of samples that can come back on that Mars sample return mission which Lori and Thomas talked about. We've also built probably the most complex mechanized system that we've ever done in the Mars program, and that's probably saying something because we've taken on some big challenges before. But our sampling and caching system is the hardware that we'll use to collect those samples. It's also extremely clean to ensure that we don't have any terrestrial contamination riding along with us when we collect those samples and we bring them back to the Earth. We've added a lot of surface autonomy, a lot of new AI, if you will, to this vehicle so that we can complete this mission on the surface. All of our Mars rovers are kind of self-driving cars to some degree, but Perseverance is going to drive 3 times faster than any previous Mars rover so that it can get that job done that we talked about in an expeditious and efficient fashion on the surface. Finally, Perseverance is really leaning forward in my mind more than any of these other vehicles which we've sent to Mars. You know, in the 1960s, right here at this facility at JPL, in fact, in the same clean room where we assembled and tested Perseverance, which you just saw in that clip, we built missions called Ranger and Surveyor. They were the precursor missions to the moon. They were human precursor missions for the Apollo astronauts. And in many ways, Perseverance serves that purpose for Mars. As I mentioned, we're carrying a lot of new landing technology, which will feed forward into that activity. We have more surface intelligence, again, more autonomy. That's a feed-forward technology as well. We're carrying a suite of ruggedized commercial high-definition video cameras. We're going to be able to watch ourselves for the first time land on another planet. We're carrying microphones to the surface of Mars. This will be the first time we've been able to put that human sensory capability on the surface and see what we get. All those are very exciting. We have a weather station which will tell us a lot about the dust and the radiation and the weather environment that astronauts would need to understand and survive for future human exploration as well. And so this is a mission that's certainly leaning forward. And I want to show you one of those technology experiments if you want to run the clip. This is a picture of the MOXIE experiment getting integrated into the rover. The rover's upside down, and as you can see, the MOXIE experiment is getting craned into the belly of the vehicle. Now, what is MOXIE? MOXIE is something called an in situ resource utilization experiment, which is kind of a fancy way of saying living off the land. This is an experiment that will actually create oxygen on the surface of Mars by ingesting the Martian atmosphere, the carbon dioxide, dissociating it using a process called electrolysis, and creating pure oxygen. Now, this is a scaled experiment to demonstrate this technology for future human exploration, both obviously for life support purposes, but the oxygen is also important as an oxidizer for fuel to bring those human missions back to the Earth. And so all of that is really an exciting and new aspect to the mission. Now, none of these things really happen And one more clip, please. On the next clip, I want to take you through one of our stars, actually, here, before I go to the next piece here. This is the Ingenuity helicopter. Thank you. As most of you know, Ingenuity is being carried on the belly of the vehicle. We'll find a good place to deploy it on the surface of Mars. We'll drive off to a standoff distance, and then we will become the official photographer for Ingenuity as it attempts to do something that's never been done before, which is powered flight on another planet. You know, this is a technology that's really going to open up a new exploration modality for us, very much like the rovers did 20 years ago when we flew Sojourner on the first mission to Mars. So none of these things actually happen without a lot of help. And I just want to acknowledge the many industry partners that we've had along the way. There are over 1,000 suppliers that have provided hardware for this mission. They're located in over 500 different cities, 44 different states. Pretty much every NASA center has contributed in one fashion or another to this mission. And in fact, internationally, we have educational facilities and universities, as well as additional suppliers that provide both engineering and science hardware for this mission. So this is certainly a team effort. And every mission deals with challenges at one point or another. And frankly, after having been doing this for 3 decades or so, I thought I had seen just about everything until about a year ago when I was proven wrong, and we all had to face the global pandemic. Now, this is something that happened right during the final processing for the spacecraft down at Kennedy Space Center. We had to react quickly. The teams had to figure out how to both keep the teams and their families safe, as well as continue to make progress for the launch, as Thomas indicated. It was really the first time during the entire development where I felt that the launch was in actually some jeopardy. It was just so comprehensive and so new. And so many teams came together to help us across the agency. Other NASA centers helped get us hardware and people down to Kennedy Space Center. The headquarters team stepped in, both Lori and Thomas specifically, and others, to help us get through that period. And of course, the team rose to the challenge and got us to the launch pad. And we've managed to fly the spacecraft to a point here where we're just a few weeks away now from landing. I asked the team in the spring of last year to come up with something that would symbolize, to mark this challenge, and to thank, in particular, the frontline workers, the medical community that were out there doing their job. And the team designed this. We call it our COVID plate. As you can see, it's got a representation of the Earth, the globe, all of us facing this challenge together. It's got a symbol of the spacecraft leaving the Earth, heading to Mars, and of course, all of this supported by the familiar staff and serpent of the medical community. We're proudly carrying this plate to Mars so that we'll remember back here on the Earth in the year 2020 and 21 that there was a community that stepped up and bravely did their jobs so that we could do ours. I want to pass the baton at this point over to Al Chen. He is our entry, descent, and landing lead. He's going to tell you a little bit about this activity that we're going to go through here in just a few weeks. It's one of the most difficult maneuvers in our business, and he will take you through the steps and the challenges that we have coming up in just a few weeks. Al.
Thanks, Matt. I don't think I'm exaggerating when I say that entry, descent, and landing is the most critical and most dangerous part of the mission. Success is never assured, and that's especially true when we're trying to land the biggest, heaviest, and most complicated rover we've ever built to the most dangerous site we've ever attempted to land at. If you take a look at this next little video here, you get a little taste of what those 7 minutes of entry, descent, and landing will look like in just about 3 weeks. Just looking at and thinking about landing really gets the blood flowing for me. Landing on Mars is really all about finding a way to stop, and stop in a safe place. Perseverance first hits the atmosphere, going almost 12,000, a little over 12,000 miles per hour, and streaks across the sky like a meteor, using that atmosphere to slow down. During that entry, it's got to survive the intense heating and deceleration of that period, while also using thrusters to steer toward the landing target to make sure we go to the right place. After slowing down to supersonic speeds, Perseverance will deploy a large 70-foot diameter parachute while still traveling almost twice the speed of sound. That'll slow the spacecraft down even further. While coming down on the parachute, Perseverance needs to figure out where it is. To do that, it'll jettison the heat shield that protected us during entry, and it'll use a radar and a new system we call terrain relative navigation to help figure out where it is. But the parachute alone isn't enough to slow down Perseverance for landing. In fact, the spacecraft is still going more than 160 miles per hour when the parachute is done, slowing it down. That's about as fast as a skydiver would be going if he jumped out of a plane here on Earth and headed straight for the ground head down without a parachute. So at an altitude of a little over a mile or so, Perseverance will fire up its engines, fly to a safe spot identified by that terrain relative navigation system, and slow down to about 1.5 miles per hour right above it. And then it's ready for sky crane. Perseverance will lower itself, much like Curiosity did, from that rocket-powered jetpack descent stage and maneuver in for a gentle touchdown right on its wheels, at a speed slower than I walk. And because of how long it takes for radio signals to get back from Mars all the way to Earth, Perseverance has to do this all on her own. We can't help it during this period. So as you'll hear from Ken and Bryony, Jezero Crater is a great place, a magnificent place for science. But when I look at it from a landing perspective, I see danger. It's a formidable challenge. The site is replete with steep cliffsides that we're having to run right through the middle of the landing site. There's sand, there's boulders, there's impact craters. All of these would be a bad day if we touched down on them. So two new technologies that we've added for Perseverance since Curiosity make it possible for us to go to Jezero safely. The first is something we call range trigger. With range trigger, we've given Perseverance the ability to decide for herself when to deploy the parachute based on where she is. That helps us shrink the landing error ellipse, or all the areas that we can come down in, as you can kind of see in this graphic here. When coupled with the guided entry system we had on Curiosity, giving Perseverance the ability to choose where to deploy that parachute really shrinks the area that we might come down in and lets us land in a tight space like Jezero Crater. The second major technology we've added is terrain relative navigation. With TRN, terrain relative navigation, we've given Perseverance eyes and a map. I'm not sure most people do this anymore, but at least you used to be able to drive around in your car and look at a map and look out the window and see what you saw out from the window and match it up to what you have on your map and figure out where you are based on that. That's kind of what we're asking Perseverance to do too with terrain relative navigation. She's got an extra brain in there to help figure out where she's going, and an extra camera in there to give her eyes to see what's out there and match it up with that onboard map. Once she's figured out where she is, she can fly to a safe spot nearby. We've actually tested out this system out here in California, out over places like Death Valley, as this next clip will show. Here in this clip, you can see us mount that terrain relative navigation system on the front of a helicopter, so we could fly it over all sorts of different kinds of terrain that it might see, terrain that's similar to Mars. So here we are in Death Valley. Out there, it's on this gimbal in front of the helicopter, trying to mimic the kinds of rates and altitudes that we'd see on the way down on Mars. Here you'll see the system actually comparing what it sees from the camera that's looking down with an onboard map that's derived from satellite imagery, much like we hope to do on Mars. It matches up landmarks that it sees with its camera, with its eye, with those onboard maps and what it sees from those maps to figure out where she is. That helps us get our uncertainty and where we're at down to a couple of tens of meters. When we have that information, we can use that to help us fly to a safe spot nearby once we are done with the parachute and are flying on those engines. That way we can always make sure that we land in a safe spot for the rover to touch down. If it wasn't for range trigger or trained relative navigation, we just could not go to Jezero, as Matt mentioned earlier. Finally, we have one more system that I'm really excited about to try to give people a sense of what it's like to land on Mars. We have the system that's called the EL camera system, which includes a slew of cameras, as you'll see in the next picture, and a microphone. We've got cameras that are looking up at the parachute, so we'll see that supersonic parachute inflate. This will be really the first time we've ever seen that occur on another planet. We've got a rover download camera that'll allow us to see the ground rushing up at us as we go hurtling toward the ground. And then we also have cameras on the descent stage, that rocket-powered jetpack, looking down at the rover, and then at the rover, looking back up at the descent stage. So we'll be able to really see what sky crane is like during that period and see that rover descend from the descent stage and be craned right down to the surface. Additionally, with that microphone system, we'll be able to hear what it's like and what it sounds like when we're coming through those 7 minutes of entry, descent, and landing. So the entry, descent, and landing team is really excited for the challenge that we have in a few weeks, and we're really looking forward to bringing everyone for the ride. But while that'll be the end of our journey with Perseverance, the entry, descent, and landing team's journey, that's really just the beginning of the adventure on the surface and Perseverance's adventure and its mission. So to talk about some more, I'll hand that over to Ken Farley here.
Thanks, Al. 3.5 billion years ago, Mars was very similar to Earth in several important ways. It had a substantial atmosphere, it had lakes and rivers on its surface, and it had habitable environments, places where organisms that we know about on Earth today could have thrived. These are the only habitable environments that are known beyond the Earth. The central focus of the Mars 2020 mission is to explore one such environment and to see if it hosted Martian life. We're going to Jezero Crater. I much appreciate the efforts of the engineering team to get us to a dangerous landing site. It is a spectacular landing site. It once held a lake, and what we're going to do as soon as we get there is to explore the rocks that were deposited in that lake for biosignatures, for evidence of ancient life. The best and most promising samples will be collected into sample tubes that look like this. And I'm really happy I can show this. This is a truly elegant piece of hardware, and it's also beautiful. We will collect the samples directly into tubes like this, and they can be brought back to Earth by a future mission, which will allow scientists to analyze the samples in them using the full arsenal of capabilities that exist in terrestrial laboratories. Mars 2020 is the first mission which explicitly is seeking the signs of ancient life, and the first mission in which samples will be located and packaged for return to Earth from another planet. It's also the first mission in which a significant part of the science team was selected specifically to represent the interests of the future. And that's because the samples will return to Earth sometime in the 2030s. And as Lori said, they will be analyzed for decades after that. And what that means is that the scientists that are presently on the Mars 2020 science team are unlikely to be the ones that analyze the samples. The scientists who will analyze these samples are in school today. They might not even be born yet. And so it's important to understand that Mars 2020 is going to be doing its mission over the course of the next few years, but it is also a serious investment in the future of our science. I have the first graphic. Mars today is very cold, it's very dry, and it is completely inhospitable on its surface to life as we know it. The lake that once existed in Jezero is long gone, and here's what it looks like now. I love this image because it is so easy to see what's going on if you look closely. What you see in this image In the background, the hills, that's the rim of Jezero crater. And I hope you can see the canyon that is cut through that rim. That canyon was cut by a river that flowed onto the floor of Jezero crater and deposited that large delta when it hit the slack water of a lake. That delta tells us absolutely clearly there was a lake here. This was a very large lake. It was about 30 miles across, which is about the size of Lake Tahoe, and it was hundreds of feet deep. And I should point out, for scale in this image, the crater about in the middle of the image, that is about 1 kilometer across. It's a very useful marker for us. So we will land, and we will have to check out the rover. It'll take some time to establish that the rover has arrived after its long and dangerous journey with everything functioning properly. So the first thing we have to do is we have to check out the rover, make sure everything works, check out the science instruments, calibrate the science instruments, and fly the Ingenuity helicopter. All that's going to take several months, during which science is not the primary focus of the mission. As soon as we're done with that phase, we are ready to go. And what we will do then is explore the geology, which means we will look at the rocks that were deposited in this lake and its surroundings to understand what they tell us about the history of the planet, and especially about the history of this habitable environment. And then we will use the very powerful instruments on the rover to look for biosignatures, to look for these leavings of ancient life. And we will collect about 40 samples into the tubes that I just showed. And ultimately, these will be transferred to the follow-on mission that can bring them back. The team has been studying this site for quite a few years now, and what we've come up with as a possible traverse is shown in this image here. And as I said, we don't know exactly where we're going to land, but it is likely that we will relatively quickly move on to the green line that you see here. This is a pathway that connects together all of the different habitable environments that we think existed within this lake and in its surroundings. You can see that we will drive up onto the delta and explore the features in the delta, and then move up to possible shoreline environments, and you'll hear more about those from Bryony in just a minute. And then we will climb up the crater rim, and just for reference, that crater rim is several thousand feet high. So it's important for me to point out this is a very ambitious undertaking. I sometimes call it an epic journey. It is about 15 miles long, so this is a long traverse. It'll take many years for us to do this. And the reason we do this, though, is that this will allow us to come up with the best possible set of samples to be brought back to Earth, to answer the major questions that we have about Mars and about life. What would a Martian biosignature look like? Well, it might look like this. This is a stromatolite. It is a biosignature of microbial life, and such biosignatures are the oldest undisputed evidence of life on Earth. Rocks that are 3.5 billion years old that occur in Western Australia and several other places tell us that life was abundant on Earth 3.5 billion years ago. And they tell us that life at that time was only microbial. There was no complex life at that time. And that's important because if we use Earth as an analogy to what to look for on Mars, we should not be looking for things like fossil teeth or fossil bones or fossil leaves, because life took too long to develop those kind of capabilities to be present in the rocks at Jezero crater. So we will look for stromatolites, and I particularly like stromatolites because they can be large enough that you can see with your eyes. We can see with the cameras on the rover. That will allow us to locate them in this very large study environment. We also have capabilities on the rover to study the rocks microscopically in a very small patch, to look for structures at a much smaller scale that could have been produced by microbial life. And we have the ability to detect and map organic matter. And of course, organic matter is important because all life as we know it is made out of organic matter. So those are the kinds of ways that we will try to identify ancient biosignatures on Mars. People often ask, what is the likelihood that we will find evidence of ancient life? What is the likelihood that life existed on Mars? And of course, we don't know the answer to that. But I'd like to point out that those rocks that are 3.5 billion years old on Earth that have biosignatures in them, that have stromatolites in them, were deposited by microbes in the bottom of shallow lakes and seas. The Perseverance rover is about to land in a former lake 3.5 billion years old. This is a tantalizing similarity. It would, of course, be a fabulous scientific discovery to find that life existed beyond Earth. It would also be a very important discovery for humanity in general. We all know that this is one of those questions that people have pondered for a long time. It's also important to understand that even if we don't find evidence of life, that's important too. It's important because it seems that all habitable environments that have been studied in detail are inhabited. If we do a deep exploration of Jezero crater with the rover and its instruments, and with the samples when they come back to Earth, and we find no evidence of life, we will have shown that in at least one place there is a habitable environment that is not inhabited. That would be a unique and important scientific discovery if that's what we find. It would tell us something important, that habitability alone is not sufficient, that something else has to be present, some perhaps magic spark that causes life to occur. And we'll need to think about that as we consider other potentially habitable environments in our solar system and also in the very large number of extrasolar planets that likely exist in the habitable zone. So now I'd like to turn it over to Bryony Horgan, who is a member of our science team. She's going to tell us more about the Jezero crater environment.
Great, thanks, Ken. Yeah, so this first image you're seeing on the screen, this is an image that you would see of Jezero if you were flying over it in an airplane or landing on it in a spacecraft. This is kind of the view that Perseverance will see with its cameras during descent. And I think it's a really nice illustration of what Ken was talking about, that Mars today is this cold, dry, and inhospitable place, but that there's really clear evidence on the surface that it did, and that's the delta in Jezero. So you can very clearly see the river cutting through the crater rim and depositing this delta on the crater floor. And, you know, one of the things I love about being a geologist, at least pre-COVID, was the ability to get in a plane and fly over the United States and look down and imagine what the surface looked like millions of years ago based on what I could see. And in this image, I mean, you can do that, right? You can start to imagine what Jezero used to look like, but billions of years ago, 3 to 4 billion years ago. And the reason we can do that, and the reason we're hoping to do that even better on the ground with Perseverance, is because the geology in Jezero crater is so exceptionally well preserved. You know, it's very clear that the delta was formed time so long ago when Mars was warmer and wetter and more hospitable to life. And in fact, the delta itself is one of our first targets in our search for ancient life. And that's because as deltas form and rivers travel across the surrounding landscape, you have all this, rain in the rivers, transporting any kind of organic or biological material into the lake. And those organic materials get concentrated in the bottom of the lake in the muds. And we think, based on looking at orbital data of the delta, that those muds that could contain signs of organic materials and life are actually preserved at the base of the delta, at the cliffs in the front of the delta in Jezero crater. But there's more to Jezero than just the delta itself, and you can see that in this image it's shown now with all these beautiful colors. And so these colors are not what you would see with your naked eye looking at Jezero. In fact, here we've taken colors, we've used colors here to indicate what kind of minerals we see on the surface using spectrometers in orbit on our satellites at Mars. And here, this is telling us that Jezero is a very diverse place, has lots of really great geology, different over the place. However, what's really important here is the green, and the green here indicates carbonate minerals. Carbonate minerals are important on Mars or on Earth because they form when carbon dioxide in the atmosphere interacts with water and rocks and then precipitates out these minerals. On Earth, we see them all over the place. They're one of the most common deposits you get out of lakes and oceans, and so we're excited to find them on Mars. They tell us that water was once present at the surface. But in Jezero in particular, we're very excited about the carbonates. And you can see that there's kind of green everywhere here, but in particular, there's this kind of bathtub ring looking zone of carbonates just between the delta and the crater rim. And we think that might correspond to the ancient shorelines of ancient Lake Jezero. So places, ancient beaches you could have sat on along the shore of Lake Jezero. And so that's really interesting that the carbonates are in that location, because that could mean that they formed along the ancient beaches in the lake itself. And that's really great because carbonates, when they form in the lake, when they precipitate as a mineral out of the water, can actually trap whatever's living in there. And so in this next image, you can see an image of what we think ancient Lake Jezero might have looked like. Of course, this is back on Earth. This is a place called Lake Salda in southwestern Turkey. And here, this is a lake that we think is chemically very similar to what ancient Lake Jezero might have been like. And you can see it's this beautiful blue lake. But what's really interesting are all these weird looking boulders at the very front of the image. These sort of novel looking boulders are actually covered in microbial mats. These are actually modern stromatolite-like boulders that are forming today due to interactions between microbial mats, microbes living in the lake, and the minerals, the carbonate minerals that are precipitating out of this lake. This is the kind of thing we hope to be able to find in Jezero Crater. So in the next image, you'll see a view, just turning to the right, looking away from those stromatolite-like forms, looking down the shoreline of Lake Salda. You can see all these beautiful white carbonate minerals. And again, this is what we hope we'll find in that kind of green ring you saw just by the rim of Jezero Crater. We hope we'll find preserved ancient beach deposits. And in fact, in this image, in the upper right, you can see all these big white cliffs. Those are lithified beach deposits from when the lake level was a little higher. And we hope we'll find those exact same things in Jezero Crater, and that Perseverance can actually rove along these ancient beach deposits looking for signs of ancient life trapped in these carbonate minerals. Okay, so that's why we're so excited about Jezero Crater, because it has so many different ways that it could preserve signs of life. So what will we actually see once we land? Well, here's a great video showing the kind of perspective view we might get from the rover. This is, say, imagine if we landed on the crater floor in front of the delta. So the cliffs you can see in this video are actually the front of the delta. And that, again, will be one of our first targets to look for signs of organic material and other signs of life in the lake bottom muds preserved at the front of the delta. And we might land on the delta. That's also a possibility, but then we'll end up with a fantastic view looking out over the crater floor. Either way, we're going to have, we'll be landing on just amazing rocks and be able to do fantastic science right away. So on the science team, we are incredibly excited to actually get on the ground and start doing fantastic geology. All right, thanks, and I'll send it back to you, JPL.
Thanks, Bryony. We are now ready to take media questions. Remember to press *1 to get put in the queue, and please direct your questions to one of the panelists. We're also taking questions through the Countdown to Mars hashtag. To start is Bill Harwood from CBS News. All right, Bill Harwood from CBS News. All right, we're going to move on to Marina Corin from The Atlantic. Marina, are you there?
Hi, I am. Can you hear me?
Yes, we can.
Hi. This is a question to whoever wants to talk about ingenuity. What lessons are you taking away from the failure of the mole on InSight? The mole and the helicopter are obviously very different instruments, but they are a little similar in that they are more on the experimental side and doing things that haven't been done on Mars before. So what have you learned from what happened with the mole?
Well, let's see. I could talk certainly about ingenuity and how we're approaching it as a technology experiment. I'm not the right person to talk about the InSight mission, frankly. But I will say, as I said, I think during the initial opening comments, that when we take on these new technologies, that's why we're taking them on, because they're new, because they're difficult, because we haven't done them before. The helicopter Ingenuity it's a high-risk, high-reward endeavor. It's something we have not tried. And there's always going to be some probability of an issue. But that's why we're doing it. We'll learn from the issue if it occurs. I think when we do develop these systems, we put a lot of thought into what we need to do to test them here on the Earth. And Ingenuity is a great example of that. We flew this helicopter in Mars-like atmospheric conditions in our chamber many times during the initial development and during the final activities, trying to get it ready to fly. We did a lot of work to verify that this hardware was going to survive that very difficult Martian environment. The thermal cycles are very punishing on electronics and hardware, and so we test that hardware before we send it to Mars. We look at things like dust. The dust on Mars is very fine. It's like talcum powder, and it can get into our mechanisms, including the things that, type of mechanisms that Ingenuity needs to fly. So we work hard to test and look at all those environments and all those risk factors.
We had there, and if we did it again, we would do it exactly the way we did it. And it's for the very reason that Matt just talked about, and that is that it's a perfectly good question that was asked with all the information that was, known at this time, with all the testing that was there, and once we landed successfully with the full commitment of the entire team trying to make it work, and in fact, in this case, finding that the physical properties of that soil, right there where we're trying to, where the mole is trying to hammer itself down, were not the same as we've seen before in other cases and in other places on Mars. And so we tried everything we could, and after trying everything we could think of, we said, the experiment is over. We learned a lot, and trust me, the next time we want to go back with a similar type of experiment, of course we want to try again. And we're really excited once the European rover launches in a year or so. They will also have kind of a way to get below the ground, so we look forward to what they're learning from that. We'll learn from these experiences, and just like Matt said, this is exploration. Those are the characteristics of exploration. What will we learn about Ingenuity? There's some environmental factors we don't fully know. We've never really experienced at the level of a flying system. But the point is, we have all the data from the surface of Mars in our that is known to humanity in our databases, and from various missions. And just like Matt said, everything that could be done was done with this particular vehicle to make it successful. So we look forward to it.
Thank you. And it appears that Bill Harwood from CBS News is back on the line. Bill, can you hear us?
Thank you very much. That was a mistake on my end. I just wanted to follow up something with Ken Farley, if I can, really briefly. You were talking about the possibility of negative results. You don't know if you'll find any biosignatures, but are there any practical implications to that? And what I mean is, you'd still send the landing craft, I assume, to pick up cache samples, even if you didn't see any obvious biosignatures. But would a negative result in any way, while it has scientific value, would you worry that might impact political support, ongoing support for additional missions down the road, given the high cost and other targets in the solar system that some might want to explore? Thanks.
Yeah, I don't think we should expect a definitive answer of the type that I was offering from the instruments that are on board the rover. The kinds of capabilities that are required to make a definitive assessment, was this habitable environment not inhabited? The kinds of instruments that are required to do that are the kinds of instruments we have on Earth. That's why sample return is necessary. So we generally suggest that we have the capability to detect potential biosignatures, things that might be biogenic, but it will be very hard for us to prove that. So I don't think the absence of something that we can wave in our hands and say we have found evidence of life, I don't think that should be considered at all a necessity for sample return.
Thanks, Ken. Up next, we have Mike Wall from space.com.
Thank you all. Dan, this one's probably for Matt. Could you just give us like an idea of what the next 3 weeks are actually going to be like for you guys as you prepare for the EDL? Is everything pretty much set now, or are there lots of sort of preparatory tests that you need to do, lots of checkouts that you need to do to sort of get ready for that? Thanks.
Yeah, I can say a few words, and I think what I'll do is I'll turn it over to Al Chen to say a few words. For me personally, I'm going to get a haircut because we haven't been able to get a haircut for a long time in Los Angeles. So that's one thing I'm going to do. I think, the team has a number of well-understood sets of activities that they need to get through on the vehicle. And I think Al is the best person to go ahead and talk us through some of that.
Sure, Matt. Right now we're finishing the last tests really of all the EDL hardware, the last checkouts we have before landing. So we're finishing up that this week. Next week we're going to do what's called a cold boot. We're kind of basically, in some sense, erasing the memory of the past 6 months on the vehicle so that we get a system that's very much like we bring up our testing systems here, our test beds, in which we bring them up from powered off. So we want to make sure that we fly the vehicle just like we test it. So that's really what the purpose of next week is to try to configure the spacecraft as close to the way we test it as possible. Past that, we have a few more maneuvers that we can do to make sure we're right in the right place to start EDL, the entry, descent, and landing, at the right time. Additionally, we have the ability to give the spacecraft more information about where it is that it'll use when it's in the atmosphere. I spoke earlier of the fact that we're allowing Perseverance to figure out when to deploy her own parachute. We need to seed her with the best information of where she is to begin EDL so she can make that decision well. So those are kind of the big activities that are going on. Basically, in that last week, it's all about making sure that we're all primed and in the best position to succeed, almost literally, for EDL.
Thanks, Al. And up next is Steve Gregory from KFI.
Thank you very much. This might be for Ken. I'm really curious about the microphones on board. Whose idea was it to install microphones? And what exactly is it you hope to learn from microphones? Thank you very much.
Yeah, let me just point out there are 2 microphones that are on board the rover. One of them is associated with the package of sensors that will record EDL. And I will turn it to Matt to comment on that. But there's a second microphone that is part of the SuperCam instrument, and we don't really know what it will be able to record, but one of the rationales for doing it is there's a laser on SuperCam that will interact with rock at a distance, and it is likely that that interaction will make noise that we can record with the microphone, and we can, for example, potentially learn about surface coatings and other characteristics of those rocks that we could not learn any other way.
Yeah, so as Ken said, there are 2 microphones, the one he mentioned on SuperCam, and then there is one associated with the cameras that Al talked about, what we call the EDL cameras. These are commercial ruggedized cameras, and they came with, or they gave us the capability essentially to almost for free plug in a microphone sensor to that system. And so we took it. You know, we thought it would be exciting to have, as I said before, that new human sense along with us for the ride. We expect to have that microphone, well, it will be active during entry, descent, and landing. So we're hoping to hear a lot of pyrotechnics being fired, a lot of separations and deployments happening, maybe some wind, you know, after the heat shield comes off. So we're hoping to hear essentially the sounds of EDL, and we believe engines firing maybe. We'll see what we hear. That's part of the reason we're taking it, because it's new and we haven't done it before, and we want to understand what we get from it. And there will probably be some engineering aspects, you know, that will derive from that data. If that microphone survives on the surface, and I suspect it probably will, then we'll also use that microphone just to listen to the sounds of the vehicle. We have, for instance, a pump that pumps fluid around the vehicle, Freon around the vehicle to keep it warm. And so we'll listen to see how that pump sounds, just like anybody would, you know, from a health perspective on on an industrial pump, for instance. We should be able to hear the wheels crunching over the surface as we drive. And I think we're going to hear that big rotary percussive drill, the big jackhammer drill out on the end of the robot arm. I think we'll hear that as well with that microphone. So, those are some of the things we hope to get with the microphone.
Modern cells, we could likely detect them with the instruments that we have, but we would not be able to tell that they were alive. So it is possible that if life existed there, we could see it, but we couldn't tell if it was alive.
Thanks, Ken. We now have the phone lines. Paul Brinkman from UPI. Paul, can you hear us? All right, we're going to move on to Irene Klotz from Aviation Week.
Hi, thanks very much. I have an engineering question and a science question. The engineering question for Alan is, with the range trigger and the TRN, how much fly time does that buy for Perseverance? What sort of time frame could the landing occur in? And I'm going to go ahead and ask the science question, if that's all right. It's kind of follows a little bit what Bill, I think, was trying to get at, is after Viking, there were no Mars missions for 20 years or so, when that proved to not find life, or most people feel it didn't find life. Maybe Ken or anyone else, can you put into context the experiments that are going to be done with Perseverance in light of what was done with not only Viking, but also all the scientific discussion about the ALH 8401 meteorite? Thanks.
I think the first question was about how much uncertainty there is and how long it takes to land, if I got that right.
Right. So how much time would you have to, it could land between this time and this time based on the ability of the rover to fly itself?
Gotcha. We land, typically nominally about in 7 minutes from the top of the atmosphere to the bottom. The uncertainty in that timing can vary about half a minute to a minute or so, depending on what the conditions are. As you mentioned, right, there are lots of things that drive that uncertainty. In particular, it's the atmosphere. What the atmosphere happens to be like that day, what the weather really happens to be like that day, can affect how fast we come down. But it's typically between a half minute and a minute of uncertainty.
Irene, I know you had a science question. Perhaps Lori Glaze could answer it for you.
I can certainly try to answer that question. We've really, since the Viking days, really tried to take a very methodical approach to how we go about trying to ask the questions about whether or not life might exist someplace on another planet or another location besides Earth. We've taken a very, very, as I said, methodical approach, first starting with trying to follow the water on Mars, trying to understand just what the environments were like on Mars in the past and today, and that evolution over time, trying to understand just when the water was present, in what quantities, whether it was liquid on the surface, was it acidic, was it a more benign type of water that might be conducive or similar to the types of water we have on Earth that were conducive to life. And we've done this, we've taken these steps, and we were able to identify that water was present on Mars. And then we took the next steps and said, well, let's go to some places where we believe water was present in the past, such as Curiosity in Gale Crater, able to identify, looked for and identify organic molecules that were present, looked for complex organic molecules that could be the early building blocks, potentially, of life. So again, kind of a stepwise approach to trying to best position ourselves to be prepared to look in the best places we can to try and find or look for those signatures of where life might have existed. And all of those steps have driven us and taken us to this point that Ken described, which was to identify Jezero Crater as a place where we believe there was standing water in the crater, within the Jezero Crater, and that there was actually a river flowing into that crater that would have been depositing its sediments from a large catchment area, and that if life had started to form 3.5 billion years ago, as it was beginning to form on Earth, same time frame, if it was happening at that time, there's a very high probability that if it were there, it should have been contained in those sediments and could potentially have been deposited in the deposit there in the river delta that's inside Jezero Crater. And so we feel like we've positioned ourselves in as best place as we can with the information that we have to look in the best spot that we know is available. And again, as Ken says, there's a chance that we may not find it there, but that's an important science discovery in and of itself. And there's certainly many, many other incredibly important science questions to answer at Mars beyond just the astrobiology questions, just trying to understand how planets form, how they evolve over time, how their climates change over time. And so I think Mars is an incredibly compelling destination for many, many reasons, and I fully expect us to continue that exploration well into the future.
Thank you, Lori. Up next is Keith Coing from NASA Watch.
Hi, can you hear me?
Yes, we can.
Okay, my question should be addressed to some people who are not present on this panel, so I'm going to direct it to Dr. Zabukin instead. The Mars 2020 mission involves the flight of the Ingenuity helicopter drone, which is a joint effort by the Science Mission Directorate, the Aeronautics Research Mission Directorate, and the Space Technology Mission Directorate. We just heard a quote from the new vice president, and I'm wondering, at a time when this new administration talks about a, quote, whole of government approach, one would think that the whole of NASA would be using their various outreach tools to talk about this helicopter and the overall mission. Yet you don't hear anything from the Aeronautics or Technology Mission Directorates, and their audiences aren't hearing about this. This is a little odd, since this rover and its helicopter have relevance to virtually everything NASA does and applicability to things in many people's everyday lives. So why isn't the whole of NASA doing their best to highlight the diverse capabilities of this mission?
Hey, thanks so much, Keith, for the question. As always, you're one of the best experts at looking at how we communicate and also helping us kind of identify places where, in fact, we can get better. But let me just talk about this experiment. This is a whole of NASA, whole of government kind of approach. There's never been, a rover that was developed with all the parts of NASA really being involved. I think Matt already told us that experts from all these domains were actively present, and that includes aeronautics, the space tech people, looking at Medley, also an experiment on the way down, looking at entry, descent, and landing, and discovering science there. And then, of course, on human exploration with the MOXIE experiment that was being talked about, and, of course, science. So it really has the characteristics that you just talked about. And it's also true, I met with both associate administrators, both the one from Space Tech and from aeronautics this morning, precisely on this point, because I just really believe it's just a huge opportunity for us, and there's tremendous excitement on all of these. And this will not stop with this one. Look at Dragonfly that we're developing, going to Titan, another flying object. Look at other destinations that are under consideration. And as we go forward, this kind of whole of NASA, whole of government approach, just like we're modeling here in this particular vehicle, is really an overarching theme of what you're going to see in communications across. And yes, as we go forward, we're going to be excited to kind of learn from each other. And, I do the same as I look at our breakthroughs in space tech, trying to really cheer from our accounts in science the same way, because we are really on the same team. So thanks for that. Yes, it's truly, like you said, whole of NASA, whole of government mission, like there has never really been before.
Thank you. And now we have a social media question. Tammy on Twitter asks, how do you land Perseverance on a 45-kilometer spot when Mars is rotating? How do you get it to the right side of Mars facing you to land?
I guess I should take that one. Yeah, it's a little tricky, right? I mean, we have to go a long way and then put the spacecraft in a position to succeed. I'm not quite sure what the best way to answer your particular question is, except to say that we're essentially targeting a particular position for Mars to kind of hit us. We're really throwing our vehicle up in front of Mars and letting Mars run into us. And that's how we target the position that we're trying to come and enter in from. Once from that position on, really, the spacecraft's on our own to fly out where we're trying to go. And that's where we use its initial guess of where we were when we came in, those parameter updates I talked about earlier. And then it'll fly its way based on that information until it determines where it is relative to the ground, using train-relative navigation and radar while on parachute. That's how it can really figure out where exactly it is, and then target a nearby safe spot to fly to with the rockets during powered flight.
Thanks for answering, Al. And up next on the phone lines is Robert Holtz from Wall Street Journal.
Thank you. Can you hear me all right?
Yes, we can.
Super. This, I guess, is a question for Thomas and Laurie. I would like for you to step back for a moment. This is, of course, the astrobiology mission. I'd like you to help my readers understand how this sits in the broader context of the question of astrobiology in our solar system and the other potentials, clouds of Venus, frozen oceans of Europa, Titan. What is the broad picture here?
I'm going to start, and then I really want Laurie to talk about this. that is that I really do believe, and I think we're totally in agreement in all of science, that astrobiology is one of the key topics in all of science that is currently at the heart of what we're doing. It's a field where the progress is occurring at the speed that's frankly breathtaking. It is what we know today and compared to 20 years ago, it's just incredible what we've learned. We talked about some of these things on Mars. We could have similar discussions about Enceladus, about Europa. We could have discussions about asteroids. We could have discussions about exoplanets. And we could have discussions about biology, where breakthroughs have occurred in the meantime. So for us, the benefit we have with NASA is we actually have the ability, using various tools, to do some of these experiments in parallel and therefore not blame against each other. And so I'm just excited that we're, of course, developing a mission to Europa and many other approaches that we're looking at in parallel, including also researchers from heliophysics, for example, looking at the effects of magnetic fields on the stability of atmospheres and so forth. But Lori, please take it from here.
Sure. So I actually really love this question because, as Thomas says, we are looking across the solar system and even beyond into the exoplanets, trying to think about astrobiology from a much broader perspective of what are all the different potential places where we should and could be looking for potentially signs of past life or current life. And of course, Mars fits nicely into that context as a place that is fairly quick to get to. It's an easy route, easy place to get to. We've got lots of practice getting there. Not to say that it's easy, but just that we've got lots of practice getting there. And we've done a lot of work over the last 20 years in the Mars exploration program of really setting the groundwork for knowing exactly where we want to go and at the kinds of questions we want to ask. But as Thomas just said, there's many other places that we're exploring in parallel that also have a lot of potential for maybe also feeding into those questions of what types of habitable environments could maybe even still host life today. Thomas mentioned Europa. We have a mission that's being planned now to launch to Europa in 2024 that's going to map out the surface of Europa and help us better understand how thick is the ice shell and is there potentially the ocean beneath that might sustain a life. And other destinations like Titan, which the Dragonfly mission we talked about just a little bit ago, is going to fly a rotorcraft to the moon of Saturn, Titan, also looking for organic molecules and potentially environments that could have been habitable at some point in time. And so all of these efforts are going on in parallel, really each one different types of environments, all trying to answer those important questions about what types of environments could host life and what environments may even still host life today.
Thank you. We now have Jonathan Amos from BBC London on the phone.
Hi, thanks for doing this. I was just looking back at my reports from the Curiosity landing, and I think the post-landing analysis showed the rover came down about a mile from the notional bullseye. And I'm wondering if you'd had range trigger and terrain relative navigation back then, how much of that error could have been reduced? I'm just trying to get a sense of how much more accurate Perseverance will be. And also for Curiosity's landing, you drew up a grid system for Gale Crater and named each square in the grid. And I'm wondering what the name is that you've given to the notional bullseye square in the Perseverance grid.
I guess I'll take the first part of that. It sounded like you were talking about the fact that we actually overshot just a little bit. Still well within our ellipse, but overshot a little bit on Curiosity. In fact, Curiosity actually knew at parachute deploy that it was a little bit past the intended parachute deploy target, but was programmed to just deploy the parachute when it hit a certain velocity. That's what's different this time with range trigger, is that once we're in a safe velocity range to deploy the parachute, it'll look at where it is, the range, and decide whether it needs to wait a little bit longer to deploy the parachute or it's hit the right place. So if we had had range trigger on Curiosity, we would have been able to eliminate a large part of that error that we saw at touchdown. So I guess the next question was what's the bullseye named these days? I'll toss that over to Ken.
Yeah, let me help if you're not familiar with this. The scientists choose names for all of their targets that we study from the rover. We have a list of names, and they're actually pulled off of existing terrestrial maps. And we are following a protocol where our names will come from national parks and preserves around the world. And I believe the most likely place we will land is called Tamanfaya, which is a national park in Spain. I think it's in the Canary Islands.
Thank you, Alan. Ken. Up next, we have a social media question. Bryony, I think this could be for you. An average American on YouTube asks, are you going to study the surface of Mars? I heard there might be water down there.
Oh, that's a great question. Yeah, so, we're looking for signs of ancient water mostly on Mars. Whether or not there's lots of water, liquid water on the surface today is still an open question when we're trying to understand, in terms of understanding modern habitability. But as, Ken talked about earlier, this mission is really about looking for signs of ancient water. And we know from all of the missions that have come before this that there was lots and lots of water on ancient Mars billions of years ago. And so that's really what we're targeting, is things that could have lived in those ancient watery environments.
Thank you. Now we have the phone lines open again to Jeff Faust from Space News.
Good afternoon. A question, I think, probably for Al Chen. I'm curious what sort of telemetry you're getting back in real time, effectively, during entry, descent, and landing itself. You talked about having a lot of these cameras on various parts of the spacecraft during reentry. I'm curious how much of that you'll be able to see live in effect as it lands. And a related question is, during previous landings, some of the most iconic scenes were in mission control, the celebrations during successful landings. I suspect with COVID, it's going to be a different scene there. I'm curious how different mission control will look for Perseverance's landing versus previous landings. Thanks.
Okay, I think I can take those. Let's see. The first question was about EDL communications and what we'll have in real time. Much like Curiosity, we are sending some signals directly back to Earth. Those are what we call X-band tones. You can think of it like a piano with 256 keys, and we use each of those keys to mean something different. So we'll have those pretty much throughout EDL until about a minute before touchdown, about time right before or right after backshell separation. Unfortunately, then, based on the geometry, Earth will likely set below the horizon of what the spacecraft can see from Mars. So we'll have those tones, up to about a minute before touchdown or so. Second, we have telemetry coming through the Mars Reconnaissance Orbiter. That team has actually managed to update their software so that they can support what we call bent pipe communications. So we can send telemetry back from Perseverance through MRO to Earth in real time. There's a little bit of latency, but not a lot of latency. Unfortunately, the rate that we can support there is only about 8 kilobits per second, which if you had dial-up like me, I'm dating myself a little bit, but is really slow. It's slower than most dial-up that folks had. So we will not be able to send things like camera data or microphone data in real time. We'll have to send that all after we land. I think the next part of your question was what mission control will look like at landing. As you surmised, right, the COVID considerations, of course, mean that we have to follow various protocols as well to make sure that we keep ourselves safe and keep each other safe. So the mission control area will definitely be less densely packed than it was for Curiosity, and certainly you'll see us wearing all the protective equipment and other pieces of equipment like these dividers that'll help us keep each other safe.
I'll just add that like every workplace, as Al mentioned, we have to instigate those protective protocols to keep each other safe. But assuming we do have confirmation, of landing, I don't think COVID's going to be able to stop us from jumping up and down and fist pumping. So you're going to see a lot of happy people, no matter what, once we get this thing on the surface safely.
Thank you. Up next is Leonard David from Scientific American.
Yes, can you hear me?
We can hear you.
Well, great. Thanks so much for doing this, and quite a team. Right team for the Red Planet. I'd like to jump ahead a bit and talk about the samples coming back, perhaps 30, 31, or I think 31. Are we still talking about a containment facility for all the specimens that would be brought back?
Lori, would you like to try to answer that?
So I can take that one. Yes, I would. Yeah. Thank you. So you asked a great question. In bringing the samples back from Mars, when we think about making sure that we protect ourselves back here on Earth in the event that potentially there might be something contained in those samples that we'd want to protect ourselves from, we are thinking about that we've been thinking about it for quite a while, and we're all now giving it very serious thought as we're really starting to begin our endeavor for Mars sample return. And we are, in fact, in the process of really evaluating and thinking about exactly what type of facility would be the best for containing those samples when they come back to Earth. There's still a lot of work to be done on exactly what that looks like, but we are, there's a broad agency-wide effort going on there, and we're actually bringing in expertise from other agencies as well to understand exactly what type of facilities would be best for that purpose. But yes, we're taking that very seriously.
Thank you. Thank you. Up next, we have Leo Enright from Irish Television.
Would be completed.
Hello, Leo. Can you hear us?
Yeah.
It's your turn for the question. All right, Leo? Leo Enright, can you hear us?
Yes, I hear you fine. Can you hear me?
Yes, it's your turn for the question.
Thanks very much, Raquel. This is for Al Chen. Just following up on a couple of questions. Is there some sort of hover time? If the vehicle arrives at a certain place after release from the back shell, can it do a Neil Armstrong? Can it zip across the surface for a few meters if it doesn't like what it's seeing? And I also have another question for Al, if I may. As a TV guy, can you tell us what can we expect in terms of early pictures? Can you please try, in best case scenario, what are you expecting in terms of pictures in the moments after landing?
Okay, so let me try those. I think the first question was about divert. As part of that terrain relative navigation system we've added to the system, right after backshell separation, we do what's called safe target selection. So the vehicle will actually try to figure out where's the nearest reachable, safest landing spot that it can go to, and then fly there. So that kind of is your Neil Armstrong moment right there, right after backshell separation. It'll use its engines to fly up to about 700 meters or so in search of the best possible place that it can reach at that point. So that is your divert there. The next question, I think, was about what we expect to get back camera-wise. After touchdown, much like we saw with Curiosity, we are taking pictures after touchdown. Assuming we are still in communication with MRO at that time and our bent pipe system is working, we expect to get back at least low-resolution images from the front and back, taking a look at both the front and back of the rover, out from the front and back of the rover. And if we have enough time, depending on exactly what time we landed, and how much additional coverage we have before MRO sets below the horizon, we expect to get some of that data, some higher resolution versions of those pictures as well. Past that, we have a data return plan for getting back some of the data from the entry, descent, and landing camera system. That's all those cameras that are taking pictures of all sorts of stuff. We may, in the best case scenario, get a little bit of a taste the next day, but more likely over the weekend, since we land on Thursday, we'll get a decent chunk of those images, not quite at the full resolution, not the full length by any means, since that's a lot of data, but at least a good first bite at it by the end of the weekend.
Great, thank you, Al. We unfortunately can't answer all of the media questions on air. For those of you with additional questions, please call JPL's Digital News and Media Office. We'll also continue to answer social media questions online. Thank you for your questions, and thank you to our panelists for joining us today. Perseverance is set to land on Mars on February 18th with commentary beginning at 11:15 a.m. Pacific Standard Time. And we are offering lots of ways to ride along with us. To join the virtual NASA social and virtual guest events, register for the Mission to Mars Student Challenge and live stream the Mars landing, visit go.nasa.gov/Mars2020 toolkit. For those of you interested in a deeper dive, we have a new press kit available online too, with lots of information and graphics describing the rover and its mission. There, you'll also have a chance to sign up to send your name to Mars on NASA's next flight to the Red Planet. And put yourself right into the action with our Perseverance photo booth. You can pose next to the rover, place yourself on our mission control, and even see what you might look like taking a selfie on the Red Planet. Again, it's all available at go.nasa.gov/Mars 2020 Toolkit. If you're on social media, join the conversation with the mission on Facebook and Twitter. Follow @NASA Persevere and use the hashtag #CountdownToMars. Thanks for watching.